Thank you. It seems we have a little trouble with the technical things. So anyway, I will introduce this workshop today. My name is Cyril Molina. I'm the president of Oakridge. And I'm glad to welcome also my friend from Horizon, Sander de Groot. And with my right hand Samuel, they're going to present this workshop, which is about the CFT approach at the conceptual phase of an SMR. This is a key step in developing the SMR. The licensing process is usually tough and requires many skills and also a special approach. So, and then we're going to focus on a very special molten salt reactor project based on the concept developed by Horizon, and that will be presented by Sander. At first, yes. So just to highlight two facts about Oakridge. So Oakridge is a multidisciplinary consultancy doing engineering for the installed base and also for the new build projects. And we have core competencies which are in safety, nuclear safety. We do deterministic safety and probabilistic safety. Also, one thing you can notice, and maybe some of you knows already that, Oakridge was the very first company in France to get the ISO 19443 certification. It's a standard which is dedicated to nuclear safety. That's just highlight the fact that it's the core competencies we have is nuclear safety. So thank you. I give the floor to Sander. Thank you, Sander. That's your turn. Thank you for having prepared this presentation.
I guess it works. Yes, perfect. Thanks. Yeah, I will try. Okay. Thank you all for attending. I will represent Horizon and present the concept. I will focus on the safety aspects of it. So it's a limited, short presentation on the safety philosophy of the Horizon reactor. If you want to know more, there's of course a lot more to tell about it. Please visit us at the startup pavilion, where we have a stand and people that can tell you more about the system and its specifications. Molten salt reactors are great, but not easy. They are great because they are of low pressure. They're very flexible. The fuel can contain all kinds of actinides, and you can use it for all kinds of fuel cycles. There's a lot of flexibility, much more than what you can do in a solid fuel reactor, where you have major limitations on what you can include. And that allows also molten salt reactors to contribute to making the most out of the nuclear materials that are there, and also reduce the long-lived waste burdens that are generated. Because the system is of low pressure, you have a nice safety feature, and it also allows you to make the system very economical. And there's a lot of flexibility in terms of the power output. It creates high temperature heat, high quality heat therefore, so you can produce electricity or support industry directly. And because the fuel is a liquid, loss of coolant is a loss of fuel, and you can make use of that in a passive way. So you can allow the fuel to relocate by gravity and create a non-critical configuration in a passive way in an emergency situation. And that safety feature is really important and allows you to make a system passively safe. The main challenge, however, with the molten salt reactor is that the molten salt itself is hot, it's chemically aggressive, and also the materials that contain the salt are exposed to radiation damage. And that combination for most of the materials is fatal. And in the Horizon view, we think that the only practical way to solve that issue is by replacing these materials in a timely manner. And you cannot also not do that just like that. You cannot open a core, look into it, pull something out, put something new in. It doesn't work like that generally. So we have decided that to make this feasible, you need to look at closed containment replacement. And this is where our cartridge concept comes from. So our reactor consists of individual cartridges, you can see that here, which together form a critical core, but only if the pump that circulates the salt is operated. So when the reactor is not operated, the salt is in the lower part of the cartridges, forming a non-critical configuration. When you start pumping, the top part of the cartridges are filled with salt, and the top part forms a critical core. And when you stop pumping, salt goes down, and the system is no longer critical. And these materials are exposed to harsh conditions, so they degrade over time. And we replace while maintaining containment. So we pull out these cartridges as a whole, and we can then bring them to a reprocessing facility where the salt is retrieved and the materials are put to waste. But it's all short-lived waste. The salt can be introduced in a reprocessing facility and cleaned up and reused. We're not doing reprocessing online. That is a key interesting feature of molten salt reactors, but we think it brings major complications in terms of replacing the materials, and it also leads to proliferation discussion. In our reactor, the cartridges produce the heat, and in the bottom part, heat exchanger is integrated within the containment and taken to a secondary centralized system that brings it then to a steam cycle or salt storage system. This cartridge approach, next to the safety features of it, also brings other advantages. If there are no cartridges in the system, there is no primary system. So the whole primary system is basically built off-site under controlled conditions in series. Also, each new core load brings you a new primary system, so you can do improvement over time. You can make a better performance. You can change your salt compositions to accommodate different demands from the fuel cycle perspectives. And also one cartridge represents the whole core. That allows also for relatively easy qualification and demonstration of the system by having one of these cartridges built and operated. Then a bit more focus on the safety aspects of this system, specifically for this talk. Basically, we have compartmented our salt volume. So we do not have a large volume in a large vessel that is difficult to handle. We have compartmented into manageable portions that each have their own double containment. The cartridges are closed, nothing goes in, nothing goes out. They are circulated, bring the heat from the core section to the heat exchanger and back, and nothing goes in or out. We have low pressures under all circumstances. We have pump action that's required to maintain criticality. It's a double contained cartridge, and we monitor the integrity of the primary containment by monitoring a gas stream that flows in between these two containments. If we measure fission products, the primary containment is leaking, but there is still a barrier left. We also have adequate passive decay heat removal. These cartridges create a relatively large surface area in the bottom part, and that is enough to get rid of the heat in a station blackout scenario where no pumps are working. All the salt goes down, and radially the decay heat can be removed effectively in a passive way. There's a thorough defense in depth philosophy in that, so we have different barriers, and when one fails, the other picks up. Of course, we can assure the quality control of our primary system by the quality control of series productions of these cartridges. And also, maybe as a last thing, also an issue mentioned regularly for molten salt reactors is that the tritium can diffuse through the primary wall. And this integrity measurement system that takes the gas from the gas caps in between these two containments also traps the tritium, so we avoid it from traveling elsewhere. So that's it. It's a system of 250 megawatt thermal, can produce 100 megawatt electric. That size is based on cartridges that we think can still be transported in a shielded cask with reasonable work. And we focus on the recycling of spent nuclear fuel in collaboration with Orano. And of course, this system allows you also to move towards breeding cycles, if so desired. But in that case, we need to maybe change the salt composition to having more uranium in it, for example, or improving the materials of the core to improve its performance. But that's for a later stage. We're focusing now on burning the waste streams that come from spent nuclear fuel from light water reactors. think that's it.
Thank you very much, Sander. You can applause. Yeah. So now we can coming to the second part of the presentation of the workshop today. You have here a wonderful picture of the great Thorazine team in Amsterdam, this picture. And so we give the floor to Samuel. Samuel gonna present some things about key aspect in nuclear safety for the molten salt reactor, SMRs for at the conceptual phase. And as he wanted to be discreet, he just forgot to put the logo on the slides. But look, when you get out of this workshop, please bring this with you. Take one. This is Monarch Butterfly with the name of the company, Oakridge, on the other side, okay? Grab one when you get out, please. Thank you. The floor is yours.
Thank you very much, Cheryl. Thank you for the introduction. Thank you for the butterflies. Thank you, Sander, for all the detailed explanation. We are very happy in Oakridge to collaborate with a high level of expertise of Thorazine team for the development of this very exciting project in the Proxima project. So I'm going to speak about safety a bit at this step. Okay. Yeah, maybe. So for the Proxima, generally speaking, we have all the common fundamental safety function, and of course, we will ensure the defense in depth. And the regulation of current and PPs under operation will be, of course, applicable to molten salt SMR. With the three-main function to retain radioactive materials, the control of the reactivity, and the removing of decay heat. So in terms of defense in depth, we will have multiple barriers, segmenting containment, and independent barriers. So we will follow all the international guidelines, and of course the vision of safety of the internet of the IEA. And MSR should demonstrate, and in particular our projects, the compliance with the safety standards. So, through three main pillars: identification of areas of novelty on these technologies, comparing to current fleet, and it's a big thing. Identification of gaps in the applicability of the safety standards and areas for further consideration. Of course, we will have to do some gaps analysis, miscellaneous gap analysis. And for the last one, sorry, I think it's not visible. Okay, this is the identification of areas where the safety standards are not applicable due to the specificity of the technology. Okay, so I'm not describing in detail this tab. This is the IEA safety standard applicable to SMR. So for some section of the standard, it is not applicable because it's only related to pressurized water reactor. So, but we will follow mainly the module relative to the software and passive system reliability. The main figures are applicable for this. Okay. So what we will have to do in the next few weeks, next few months, we will have to follow all the licensing steps with the French regulator, which is Autorité de Sûreté Nucléaire. And we will follow the general step of a reactor development project with the conceptual design under development for the first step of the concept, conceptual design, basic design, and detailed design. Of course, there is no major changes on the different main steps to develop the full reactor. We will have to take into consideration the site, because of course this reactor could be implemented on different sites everywhere in the world. So we will have to consider the information of the sites. And we will have to follow the licensing process with a different step of preparing phase with two sub-phases, screening and early review with the French regulator, on the regulatory phase with the pre-licensing and the licensing, hopefully. From the ISN point of view, the early review phase is based on some informative meetings to understand the design. The assessment will be the official position, and the pre-licensing is related to the fact of de-risking the licensing. So we will have to constitute what we call the DOS, Dossier d'Option Sûreté, which will demonstrate the safety of our concept regarding to the applicable standards. Okay, I'm going to be maybe a little bit faster on this. For the standard on safety approach, we have two different things to do the safety demonstration. There is a safety standard that we will have to apply, and we have to consider, of course, the safety approach. So for the safety standard, it's of course due to the fact that we are going to develop through the approval of the French regulation, the RATNB, which be the main standard, and we will follow the safety objectives on design and recommendation for pressurized water reactors that we will adapt with, of course, the singularity of our concept. So we will have to adapt all the objectives and all the requirements. On other documents which will be useful, the ISN guide number 22, and this is related to the design of pressurized water reactor. It has been drafted jointly by the ISN on the IRSN, Institut de Radioprotection et Sûreté Nucléaire. And we will have to adapt, of course, those requirements to our particularity. We will, the regulation highlight on three different topics: the sufficient independence between the defenses depth levels, so we will have to demonstrate this; the prevention and protection against common cause failure affecting safety system, and other things that we will have to demonstrate; and last but not least, the protection against extreme external hazards. For the safety approach, it will be the general approach, considering some radiological risk and conventional risk. The safety approach will be based on two sub-approaches: the deterministic one, what we call DSA, deterministic safety analysis, and a probabilistic one, what we call PSA, probabilistic safety analysis. For the DSA, we will consider the DBC, which means design basis condition, and the extended design with some, accident consideration, with different level, the DSCA, operating condition with multiple failure, and DSCB, operating condition with multiple failure, leading to the core melting. In our case, it won't be the core melting. Maybe it will be the failure of the cartridge. We don't know exactly the criteria at the time being, but we will have to adapt the criteria. Okay, probabilistic. I'm going to finish with this one. Probabilistic in PSA. So generally, you have to demonstrate the safety of your concept, of your final reactor, with a deterministic approach, but the probabilistic approach will arrive in complement of the deterministic approach. So the probabilistic approach consists in two things. Generally, when we speak about our pressurized water reactor, we calculate a CDF, core damage frequency, considering some different external or internal hazards. In our case, maybe we will have to change this by the cartridge rupture frequency. We will see. Or to find some equivalent criteria. And you have to verify that large of our early release frequency has extremely low probability about the length. We will have to consider the same thing. So we have started in Oakridge 3 years ago to work on this new concept to adapt our PSA to this kind of reactor through some international collaboration. Okay, so if I have only 30 seconds, we could do the safety demonstration for different equipment and for the overall operation of the plant. So there are some key aspects influencing probabilistic safety assessment, and we have different international guidelines, which this one, for example, which give all the best practices to adapt the PSA development to the molten salted reactor, generally to the SMR, but in particularly to the molten salted reactor. This is some example. I'm going to show only this one to finish. Of course, when you have a PWR in operation, you have to consider the possibility of the aircraft crash. Aircraft crash is mainly demonstrated by a PSA. And in our case, we can consider that on our small reactor, you could have an impact of an airplane. And of course, the methodology to develop the PSA in this case will be quite similar, and we will demonstrate the robustness of our concept regarding this external hazard with some international improved methodology that we will adapt to our specific case. Thank you very much.
Thank you, everyone. So I do the wrap-up words. Thank you, Sander. Thank you, Samuel, for the presentation. So you've noticed that we are in a hurry. And so if you want to know more about the presentation and see the full presentation, please contact us. Just go to the room just behind you. We can discuss a few minutes in this room, exchange business cards, and probably work together in the future. You will have also to visit our booth, Oakridge D18. This is the one which looks like a forest. It's easy, and then we can talk about nuclear engineering and other thrilling stuff. Thank you so much. Please go to the room, have a drink, and discuss with us. Thank you so much. Bye-bye.